Now that we've seen that the regression line has the smallest root mean squared error of any straight line you might use for estimation, we're going to take another look at that error that it makes and see what we can do with it. So imagine lots of points. I've just drawn one and the regression line going through them. For this point, it's not exactly on the regression line, it is a little bit off. It's this much off, and that's the error, also known as a residual. Residue is what's left over, and this error is what's left over after you've made your regression estimate. And what we want to do is get some sense of how big those errors are. As we said before, some of them are going to be positive for points that are above the line, some are going to be negative for points that are below the line, and we want to get some sense of their size regardless of their sign. And for reasons that have been discussed before in this class, what we're going to do is we're going to look at their root mean square. So the root mean square error of regression is the root mean square of all of these residuals. So now let's ponder for a second how we go about finding those. So imagine a scatter diagram of hundreds of points. Then for each point, you must first get its regression estimate, and then you must subtract, and that gives you a residual. And then you must square all of those residuals, take the mean of the squares, and then take the square root. That's a clear enough program, but let's go over that again. Hundreds of points, hundreds of corresponding regression estimates, hundreds of residuals, and then square all those hundreds of residuals, and then take the mean of those hundreds of squared residuals, and then take the square root of that mean. So hands up all those who want to do this. Yeah. No hands. I'm glad to see that, because it shows you have a healthy aversion to doing long and laborious tasks. Now, you could of course use a computer, but there's also these wonderful people called mathematicians, and mathematicians do have a way of making life very, very easy sometimes. And there is a beautiful formula for this root mean square residual, which takes almost no computation at all. There it is. The root mean square of the residuals is the square root of 1 minus r squared times the st of y. Nice simple formula, two ingredients, the st of y, which you're usually given. R is given, root 1 minus r squared is not that hard to calculate. Multiply and you're done. All the labor is saved. And not only is the formula simple, it works for every single scatter diagram. No matter what the shape of the scatter diagram, whether it's wavy or fat in places, skinny in places, no matter how horrible you make it, there is one regression line, the line that minimizes the root mean squared error, and the root mean squared error corresponding to that best line is given by this formula. Now, I'm not going to prove this formula here. I might write it up as a supplement. It requires a little bit of fearlessness with algebra. But what we're going to do is we're going to examine that formula at least qualitatively and see what it is doing. And then we're going to use it. So let's take a numerical example. I have a set of eggs. You've seen similar data before, and we're trying to estimate how big the chicks are that are going to hatch from these eggs. So the object is to estimate the weight of these birds. And we have the two averages, the two SDs, and a correlation. So what we're going to do first is make an estimate based on no information about the egg. In other words, I'm going to pretend that I didn't write that top line. We have the bottom line, and I'm asking you to estimate the weight of the chick. Well, what are you going to do? I'm not showing you the egg. Well, if I'm not showing you the egg, you're going to guess 6.43 grams. So in a picture, what's happening is this. We have the egg size along the horizontal axis and the bird's weight along the vertical. That's what you're trying to get at. The scatter diagram's all over the place. But you don't get to see the egg size, and so you are just going to, no matter what the bird is, no matter what the egg is, you are going to guess 6.43. That's the average. The red line is horizontal at the average. For every single one of these eggs, you're going to guess that the bird hatching from it is going to have weight 6.43 grams. So how far are you going to be off? Well, if that is the actual weight of the bird, you have guessed 6.43, so you're going to be off by the distance between the actual weight and the average, which is our old friend, the deviation from average. And so your root mean square error is going to be the root mean square of deviations from average, which is precisely the SD. And so there's nothing new here. What we've said is if you guess the average, then you're going to be off by the SD. But now, supposing we use what we know about the size of the egg. So now I'm going to take an egg and I'm going to tell you its size and ask you to estimate the weight of the resulting chick. Well, then you are going to use regression. You're going to say, okay, you tell me the size of the egg and I will go to my regression line and that's going to be my estimate. In other words, your estimates are now going to be on this green slanting line. And it is clearly better to use the green slanting line than the red flat line. It looks much more like the scatter diagram. And so what are the errors that you're going to make? Well, for any single point, that's the actual weight of the bird. Your estimate is going to be here on the regression line, and so you're going to be off by a residual. And so your error is going to be, well, your root mean square error is going to be the root mean square of the residuals, for which we have a formula. And I'll remind you with these numbers what that formula is. The square root of 1 minus r squared times the SD of the thing that you're trying to estimate. And we'll calculate the number, but what I want to do is I want to compare these two error sizes. Which one is smaller? It's the second one that is smaller. You see, 0.6 is a fraction, root 1 minus 0.6 squared is actually 0.8. And so if you compute the root mean square of the residuals, you get 0.32 of a gram. The error that you make overall in using the green slanting line is smaller than the error that you would have made using the flat red line. And that is exactly as you would want it to be, because there's a natural visual sense in which the green line is closer to the scatter diagram than the red line. Well, if it's a better estimate, and indeed we've said it's the best of all possible estimates among straight lines, then its error better be smaller. And the calculation shows that it is. So let's take a look at that formula again and see that it makes sense in certain cases where we can guess roughly what the answer should be. That's not the same as proving the formula, but it's reassuring. So what is the formula for? It's to give you a sense of roughly how much error you're making in the regression estimate. And what is the formula exactly? Well, it's root 1 minus r squared times the SD of the thing that you are trying to estimate. So let's take some extreme cases. R equals +1 or -1. Well, then what does the scatter diagram look like? It looks like a perfect straight line, in which case that is the regression line, and you don't make any error if you're using regression. You're going to get it exactly right, and your error is going to be 0. If you plug in +1 or -1 in here, you're going to get 1 minus 1, that's 0, and your formula is going to tell you that the error is 0, which is exactly what it should be. So it gets it right for the extremes of R. The other case where we ought to be able to guess what the answer should be is R equals 0. If R is 0, there is no linear association between the two variables. Then why, pray, are you using linear regression? You shouldn't. It won't do you any good. In fact, what it will do is exactly what you would have got had you used no information at all. You would just have guessed the average. And you can check that when R is 0, if you use regression, it is exactly the same as always predicting the average, no matter what x you are given. Well, if you always predict the average, what's your error? Your error is the SD. And if you plug in a 0 here, then all of this is just 1. And you end up with the formula saying that your error will be the SD of y when r is 0. That is what you expect. If you are doing regression using a variable that is not linearly associated with the thing that you're trying to estimate, you can't possibly do better than using no information at all. Now, the r's that you normally come across are, of course, neither exactly 0, nor exactly 1, nor exactly -1. They're somewhere in the middle. So for all other r, regression is not going to be perfect. You are going to make some error, but you're going to do better than just using the average. And for r that is not 0 and not +1 and not -1, this formula is saying, well, you take your SD of y and you're multiplying it by this, which is a proper fraction. R is a proper fraction, so is r squared, so is 1 minus r squared, and so is the square root. And so the error in regression is a fraction of the error that you would make if you simply estimated by the average. So that is all rather comforting, even though we don't know precisely why the formula has this exact form. We do know that it behaves reasonably in situations that we understand qualitatively. Well, qualitative is terrific, but it is also helpful to get to some quantitative understanding of what is going on. And so it is helpful now to get some analogies between what we know and understand well for one variable and what we now know for two variables. So with one variable, the histogram that we understand very, very well is the normal curve. What is the corresponding picture for two variables? Yep, football-shaped scatter diagram. Now, if your variable has a normal distribution and somebody says, well, can you estimate the value of that variable? You are going to estimate the average. On a football-shaped scatter diagram, where do your estimates lie? Yep, on the regression line. And so the regression line performs the same function for your football-shaped scatter as the average does for the normal curve. And we've said a million times now that an estimate has to be accompanied by a margin of error, and you know that if you guess the average, then you're going to be off by an SD. If you use a regression estimate, what are you going to be off by? The r.m.s error of regression, and that is what we are studying now. Now you understand very well on a normal curve with a given average in SD how to find percents in any range that I might come up with. You can do exactly the same thing with the scatter diagram and regions about the regression line. And we'll spend the next little while looking at examples of those. And for the first example, what I'd like you to recall is that on a normal curve, if you look at the average and then walk one SD on either side, you pick up about 68% of the distribution. So what we're going to do in two variables with a football-shaped scatter diagram, which is the analog of our normal curve, is to draw the regression line, that's my green line, and then walk up one r.m.s error and walk down one r.m.s error everywhere along the line. If I walk up one r.m.s error, I end up just about there, and that gives me a blue band on the top and a blue line at the bottom. And so this region within my two blue boundaries is the region regression line plus or minus 1 r.m.s error. And that picks up a certain fraction of the points, does it not? What fraction of the points do you think it picks up? You got it. 68%. The regression line plus or minus 1 r.m.s error contains about 68% of the points. So, well, so when you're doing estimates, you're interested in how far off your point is from the estimate. How much error are you making? If I look within this blue band, the maximum error that I am making is 1 RMS error because the estimates are in the center here. And the biggest distance within the blue band is from the regression estimate to the edge of the band. Yeah, from the regression estimate to the edge of the band, and that distance is 1 RMS error. So what we have learned is, we can say in another way, for about 68% of the points, the regression estimate is correct to within RMS error. The error is no more than 1 RMS error. You got it right to within 1 RMS error. I'm saying the same thing over and over again in many different ways. And there's nothing special about the 1 RMS errors. If you walked 2 RMS errors, then what do you think would happen? Well, you'd get a broader band, for one thing. And within the band, what percent do you think we would pick up? Average plus or minus 2 SDs on the normal curve picks up about 95%, and so no surprise. Regression line plus or minus 2 RMS errors picks up about 95% of the points. Oh, by the way, on this scatter diagram there are 500 points. So 5% of the points are outside the blue band. 5% of 500 is about 25 points, and I went through and actually counted these guys, and it's just about 25. And so in terms of estimation, what you have said is that for about 95% of the points, the estimate is correct to within 2 RMS errors. And that's all fine and dandy in the abstract. Let's put some numbers to it. So here's a distribution you've seen before. It's heights and weights and a football-shaped scatter diagram with a given correlation. And we are going to try to answer the following question. For what percent of the people roughly is the regression estimate of weight based on height correct to within 40 pounds? Why that question? Well, let's see. If I just look at the weights, their average is 160 and the SD is 20. So if I forgot about the regression estimate and I just said, well, you know, I don't care what person you're showing me, I will just guess 160 as this person's weight, then I'm going to be off by about 20 pounds. And for 95% of the people, I'm going to get my answer right to within 40 pounds, 2 SDs. If I use the regression estimate, I should be doing better, should I not? So if I use the regression estimate, then for what percent of the people am I going to get the answer right to within 40 pounds? Well, without calculation, I'm going to say the answer better be bigger than 95%. Well, how much bigger? For that, I need to do some work. And first, it's a good idea to identify the variables. So we have been using y for the variable that is being estimated. And here, what is being estimated is weight. And so y is weight. And so we are interested in errors of regression, so we better calculate the root mean square error of regression, and by formula that is square root 1 minus r squared times the SD of y. And that comes out to 17.32 pounds, which is less than your original 20 pounds, as we have said before. Okay, so what I know is that for about 68% of the people, the regression estimate gets it right to within 17.32 pounds. For about 95% of the people, the regression estimate gets it right to within twice this, and that's just under 35 pounds. So 40 pounds? Well, the question that I need to answer is, how many RMS errors is that? It's more than 2. So how many RMS errors is it? Well, just look at it relative to 1 RMS error. 40 divided by 17.32, it's 2.31 RMS errors. So what I have done is I've stood at the regression line and I have walked 2.31 RMS errors up and down. And the percent of points that I pick up will be the same as if I had stood at the center of a normal curve and then walked 2.31 SDs above and below. In other words, my answer is going to be the area between negative 2.31 and plus 2.31 under the standard normal curve. How do I find that? Yep, I use my trusty applet, and it says roughly 98%. We had said at the start that the answer is going to be bigger than 95%, and sure enough, it's quite large. It's roughly 98%. For these 98% of the people, your regression estimate is going to be correct to within 40 pounds. It may be considerably more accurate than 40 pounds. It may be completely accurate, but the error is going to be no more than 40. So that's for 98% of the people. What about those remaining poor 2%? Well, those are the people that are very far off the regression line. Those are the people for whom the error is more than 40 pounds. And so you can make precisely the same statement in a different way by saying for roughly 2% of the people, that is all those left over, the regression estimate is off by more than 40 pounds. Those are not different statements, they're exactly the same. And so here you have a quantitative use of the root mean square error of regression. It's giving you some sense of the error that you make in regression, and you can say, for this proportion, I'm going to be correct to within this much. Now, there is another way of using the root mean square error of regression in football-shaped scatter diagrams, and that is within a single vertical strip. So this is simply a recap of the data that we have for your reference. So I have heights, average SD, weights, average SD, a correlation, and we are trying to estimate weight based on height. And so I remind you, we have done the calculation that says the RMS error of regression is just about 17.32 pounds. Notice I'm being lazy and writing LB instead of the full word pounds. Okay, so what I'm going to do now is I'm going to concentrate just on those who are 6 feet tall. And I'm going to look at their weights. So if you imagine the scatter diagram, then since we're estimating weight based on height, heights are on the horizontal axis, weights are on the vertical, and I am looking at the weights of the people who are 72 inches tall. So these weights are a vertical strip, and I know their average. The average of a vertical strip is roughly where the regression line goes through the strip. So I can find the average weight of people who are 6 feet tall. How? Well, by finding a regression estimate, which we learned how to do in the last section. I'll just remind you quickly. Take what you've got, convert to standard units. Multiply the standard units by r, and that is your answer. It's in standard units. So now convert those standard units to pounds. And so what do we already know how to do? We know that if we look at the vertical strip of weights of people who are 6 feet tall, then the average of that strip is 176.7 pounds. All right, so these weights are their own little data set, and they have an average of 176.7 pounds. Well, surely they also have an SD. So what's the SD of these weights? Well, now let's see what we've got going for us. The center is on the regression line roughly. So you're measuring distances away from the regression line, and we've got a measure of that. 17.32 is roughly the vertical distance from the regression line, except this is the rough distance from the regression line throughout the scatter diagram. And if your scatter diagram was very narrow in places and very wide in places, then in the narrow places you would expect the vertical distance to be quite a bit less than 17.32, and in the very wide places you would expect it to be more. But your scatter diagram isn't like that. It's football-shaped. A football-shaped scatter diagram is homoscedastic, about the same vertical spread throughout. So, well, in that case, this r.m.s error, which represents the overall vertical distance from the regression line, can also be used within each single strip, because each single strip has the same amount of vertical spread. And so that r.m.s error can function roughly as the SD of every vertical strip, in particular the one at 72 inches. And so what have you learned at the end of that? Well, here you have the weights of all the people, average 160, SD 20. We have now focused our attention only on those who are 6 feet tall. And we know how to find their average by regression. And at this point, we also know how to find the SD of their weights using regression. And there's just a little bit more. Again, a recap, your data, the correlation, the problem. We are looking at the weights of the people who are 6 feet tall, and we have learned a couple of things already. That we can find the average of their weights by regression. We can find the SD of their weights by regression, using the fact that the diagram is football-shaped. And once again, relying on the football-shaped scatter, which I've said some time ago means bivariate normal, which has a technical definition that I won't give here. But what it allows you to do is what I know some of you desperately want to do, is to say, okay, average 176.7, SD about 17, the distribution is normal. Yes, you may assume that it is a consequence of the bivariate normal distribution. And so now what? And so where originally you were told that the weights of all of these people have a certain average in an SD and the distribution is normal, you can now take the weights of many different subsets, the people who are 72 inches tall, for example. Every vertical strip you can look at. Those weights are their own little data set, roughly normal, with an average that you can calculate and an SD that you can calculate. And once you've done that, you understand every vertical strip. You can answer any question about it. For example, of the people who are 72 inches tall, about what percent weigh more than 200 pounds? Well, what do we know about the weights of people who are 72 inches tall? Everything. We know their normal, we know their average, and we know the SD. So how do you find the percent that are over any given amount? You convert to standard units, exactly. Z. Your point minus the average divided by the SD, and that's 1.34. So what is that? 200 is 1.34 SDs above average on this vertical strip. So what percent lie above 200? Well, it's the area to the right of 1.34 on the standard curve. And that you can find from your applet, and that's about 9%. Is that a sensible answer? Well, let's see. 200 pounds. If I look at everybody, 200 pounds is 2 SDs above average. And so the percent above that is going to be 2.5%. Because within plus or minus 2 SDs, you've got 95%, so each tail is 2.5%. So if I looked at everybody, then the percent who weigh more than 200 pounds is roughly 2.5%. Who am I looking at now? I'm looking at the people who are 6 feet tall. They're quite a bit taller than average. And so because of positive association, they're quite a bit heavier than average. And so a higher proportion of them are more than 200 pounds in weight. The answer makes reasonable sense. So stepping back again to the big picture, what you started out with was a football-shaped scatter diagram and summary statistics about the two variables. What you can do with that is you can generate summary statistics about every vertical strip. And yes, of course, also every horizontal strip. And using that and the normal approximation, you can figure out proportions not only across the board, but also within each single strip. Phew, that's a lot of calculation, isn't it? Yeah, that's been quite a lot of decimals compared to most of our segments, and it will be a relief to end with another look at residuals of regression in a qualitative way and notice something interesting. And what we're going to do is draw something called the residual plot. So starting out, we will start out with a scatter diagram, and that has the original x on the horizontal axis, the original y on the vertical, and this green line is the regression line. Now corresponding to every point there is a residual. So that point is this far away from the regression line, and so there is a residual corresponding to this point. There's a residual corresponding to each of the, I believe, 500 points on the scatter diagram. And so the next thing we're going to draw is called a residual plot. That has the same horizontal axis, still x, but on the y-axis now I am plotting the residuals, the errors. And let's just see what happened to get us from this cloud to this cloud. So the pair that I like to look at are these two, because they are very clearly these two. And why is this one lower? It was about the same distance here. It's because what's being measured here is distance from the regression line, and these 2 points were almost horizontal here, but the line is sloping. So the second point is further away from the line than the first, and that's what you are seeing in this slope down here. So that point is this one here. And so what has happened is that we are looking at vertical distances from the regression line, and so the regression line has sort of been turned so that it's now the flat line, and then there's a shear that makes your oval turn into this sort of round shape. And you know, it takes a piece of mathematics to understand that. And the mathematics says that no matter what the shape of the scatter diagram, it doesn't have to be a beautiful football like I have drawn. A couple of things are true. The average of the residuals is always 0. That's why I have drawn this line at 0 right here. Do you recall when we looked at deviations from average? We said no matter what the list, no matter how horrible the list, the deviations from average would always average out to 0. The plus deviations would exactly cancel out the minus ones. Same thing with residuals. The positive residuals exactly cancel out the negatives, no matter what the shape of the scatter diagram. It takes a piece of algebra to establish, but perfectly believable once you've seen deviations from average. And it is also true that no matter what the shape of the scatter diagram, the residuals have no linear association with x. In other words, when you draw the residual plot, it is going to be flat. It cannot have a linear trend. It doesn't matter what the shape of the scatter diagram is. Your residual plot cannot show any trend or linear relation. If you have a residual plot and it looks like that, you have done something wrong, I'm sorry. And so what? Well, what we can do is we can use the residual plot to assess our regression and improve our regression. No residual plot can show trend or linearity, but residual plots can show pattern. But if they're showing pattern, then maybe your regression was not so good. The best regressions have residual plots that look like this, a formless blob. about the horizontal axis. And what is the problem with patterns? It is easiest to see by an example. So I'm going to use a famous data set, which is the average weights of women at different heights, and famous because of a strikingly high correlation, 0.995. There's the picture. So let's understand the data. There's a population of women, and what you've done is everybody who is 5 feet tall has been lumped into this point. So in fact, everybody who is 60 inches tall to the nearest even inch has been lumped into this point. And do you recall when we talked about correlation, we said that if you lump people into averages like that, you artificially increase clustering? That's exactly what has happened here. If you look at the heights and weights of the women, the picture is going to be much more fuzzy. But we're just looking at averages. And so we have this scatter diagram that looks very, very close to its regression line. And we can go yippee and be thrilled with how good our straight line is until the moment we draw a residual plot. Ouch. That is not a residual plot that makes me feel all warm and fuzzy inside. This U shape is telling me I should not have fit a straight line. So where's this U shape coming from? By the way, the plus residuals exactly cancel out the minus. The average is at 0 and there is no trend. This thing is flat by and large. But where are these points coming from? They're coming from these, which are in general above the regression line. And then you have all of these that are below, that's the U here. And then you have these 3 that are above, and that's these 3. And what you are seeing on this magnified residual scale is that this thing isn't a straight line, it's a curve. And you should have fit a curve, you should not have fit a straight line. Now some of you with sharp eyes will have seen that here already, but you'll concede that it is much easier to see on the residual plot because the scale is so much bigger. You can see nonlinearity much better, and as numerous pictures in your textbook will show you, you can see heteroscedasticity and other features of the scatter diagram much more clearly in a residual plot than you can in the original scatter diagram. And so when you're doing a regression, people tend to concentrate on the calculation in the middle. What's the equation? What's the estimate? What's the r.m.s error? What are the numbers? But always, you should start and end differently. You should start with the scatter diagram and look at it and first decide, do I really want to fit a straight line? And if in the end you have fit a straight line, you must draw the residual plot, because that will tell you whether your wanting to fit a straight line was a good idea or not. Here it absolutely wasn't. So even though I started by trying to fit a straight line, I know that I should fit a curve, and in fact the parabola will be better, the cubic is better still. So, moral of the story, never do a regression without first drawing the original scatter plot and at the end drawing a residual plot.